I continue my talk now about local maximum and local minimum. See, the talk about absolute maximum and minimum is not clear. The talk about local max and local min, to be honest, is much simpler. It's much easier. Because what is a local max and a local min? A local max and a local min differs in its definition from the absolute max and absolute min by the fact that, let's suppose our function f is defined over an open interval. It has to be open. That's what I will explain in a minute. 1 second. I will tell you what's the difference between why here f is defined over over an open interval and what confusion does that not make. It solves the confusion. It doesn't make confusion. I will explain in a second. But let's assume f is defined over an open interval containing c. We say f of c is a local max if f of c is greater than or equal to f of x for x in this open interval. It's a local min if is less than or equal to all f of x for x in this open interval. What do I mean by that? I mean, let's assume there is a function. The function looks like this. See, local max and local min means that, you know what? Choose an open interval around a point, only a small interval around the point, and if this function value is smaller than the neighbors only, then what do we have? A local min. Here, this is bigger than the neighbors, we call it a local max. This here is smaller than the neighbors, we call it a local min. Here, this is a local max, local min, local max, local min. Local, only in a small open interval around them are they required to be minimum and maximum. See here, I'm zooming in as if I'm looking at the function, not globally. I'm not looking at it as one piece far away. Instead of looking at it in one piece far away, well, how am I looking at it? I'm looking at it in a sense that I'm zooming into bits and pieces. So here, I'm not looking zoomed out to ask what is the maximum of the whole function or the minimum of the whole function. No. I'm looking, moving one step at a time. When I reach a point where I have the value is smaller than the neighbors, this means I have reached a local minimum. Here I reached at B a local max, I reached at C a local min, and I reached at D a local max. When can those things happen? When can I reach a local max or a local min? Simple, again. You can reach a local max or a local min at critical points. That's why I'm saying the discussion of local extreme values is the same as the discussion we just did. Where do we have local max and local min? We have local max and local min when either it's a normal turning point, so the derivative is 0, or it's a corner or a cusp, which means the derivative is undefined. Its maximum, it's undefined. It does not exist. The derivative is undefined. Perfect. But how is this not the same as our study about absolute maximum values? See, again, options for local max and local min are only where? Critical numbers, critical points. You tell me, what about the endpoints? Aren't they options for local max and local min? No. Why aren't they options for local max and local min. Why can't I consider them local max and local min? Because the point that we have to have as a local max and local min should be greater than or equal to f of x for an open interval containing the point. Open interval, yani it should be, the c should be here and there should be values before it and values after it. For endpoints, there are no values before, no values after. So that's why they cannot be considered as local max or local min, because of the openness of the interval. So that's why endpoints are never options for local max or local min, even if they are bigger than the ones after them or smaller than the ones after them or before them. They are not options for local max and local min. All right, they are options for absolute. Second, a function can have more than one local max, more than one local min at different places. Whereas when we're talking about absolute max and min, we can only have one absolute maximum value, which can happen at too many places, but the value is the same. Here, the local max value of both are not the same, and both of them are local max. Also, one more thing is that how will we know if it's a local max or a local min? When we did the test for absolute max and min, we put them in the table. The highest is absolute max, the lowest is absolute min. For local max and min, it doesn't work the same way. I can tell the options, but to find out which of the options is a local max and which one is a local min and which one is neither, we need to do more work. It's not as simple as the comparison that we did for absolute max and min. So finding local options for local max and local min is easier than finding options for absolute, because the options are critical numbers only. But then testing those options is easier for extreme absolute. Why? Because for absolute extreme values, we only need to substitute. The biggest is the absolute max, the lowest is the absolute min. For the local, no, we cannot test the same way. We cannot test the same way. You tell me, Mbala, you just put the numbers, the highest ones are max, the lowest one are min. No. First, we can have more than one max, more than one min. Second, believe it or not, a local max can be smaller than a local min. Let me give you a very simple example. This is a local max. This is a normal function, right? This is a local max. These are local min. This local min is higher than this one. So if I want to compare numbers, I cannot say the highest y value is a max, the lowest y value is a min. It doesn't work. So what is the technique to classify critical points into local max, local min, or neither, because the option can be this, that, or neither. What are the options? They came and said, you know what? When do we have a max, local max? Either it's like this, or like this, or it's a corner. What happens if they want to describe what is happening? What should happen? Of course, the function values here should increase to reach the top, then start decrease again. Here again, the function values should be rising, increasing. They stop, they start to decrease. The function values here should increase. They stop, they start to decrease. Whereas when we have a local min, how does a local min look like? It looks like this, or this, or this. Of course, there are variations. It could be like this, then like this. It's anything that looks like that. But what is the description happening here? It was decreasing, it stopped, it started to increase. It was decreasing, stopped, The values were decreasing, they stopped, they start to increase. Similarly for all. So obviously, the test for local max and local min depends on knowing when a function decreases and when a function increases. So I find critical numbers. If this is my critical number, point. If the function was increasing before, then started to decrease, then what do we have here? A max. If the function was decreasing before, it stopped and started to increase, what do we have here? A min. So the test for local max and local min becomes a study of what? Of when a function decreases and when it increases, which we call it the monotonicity of f. And this is the beginning of section 3.